As seen from the previous videos, entropy plays an important role in thermodynamics. Specifically, we use entropy as a way to describe how many different ways we could arrange molecules within a system. While entropy has a central role in thermodynamics, describing it may not always be straightforward. In fact, a lot of times, when we're first trying to analyze a system, we may not have an analytical way of describing the entropy a priori. So may not have analytical equation ahead of time. Right? And so throughout this course, we'll learn about the different ways in which we could relate, observables or things that we can measure into information about the entropy of the system. But in any case, even though we, for whatever sort of entropy system that we end up with, they're all going to have the same basic properties. So all entropy functions have same basic properties. Okay? All right? And so when it comes to, describing entropy, if we have some sort of function, if we take the partial derivative of entropy, these partial derivatives should all be valid. So what we'll do is we'll first just define our entropy as a function of internal energy, volume, and also the number of molecules within the system. All right, so we're going to use those as the canonical variables. If we take the partial derivative of entropy with respect to the internal energy while keeping volume and n constant, that's going to be equal to the inverse of temperature. If we take the partial derivative of entropy with respect to volume while keeping internal energy and n constant, that will give us pressure over temperature. So this P is the absolute pressure. And then, if we take the partial derivative of entropy with respect to the number of molecules in the system, while keeping everything else constant, that's going to be equal to the negative of mu over T, where this mu is the chemical potential. And so we'll talk more about, the physical meaning of each of these parameters later. All right? But for whatever function you have describing entropy, these partial derivatives are all valid. Now, another property of entropy functions is extensivity. All right? All this means is that if we have entropy, and we multiply its internal energy, volume, and n by some factor lambda, not to be confused with a Lagrange multiplier, but we're just saying this is some constant. Right? So what we're saying is if we're trying to get the entropy of something and we're multiplying, the internal energy, volume, or number of moles in the system by some constant, that's equal to just multiplying the entropy itself by that same factor. Right? And this has to do with the fact that the entropy will scale with system size. Right? So if you're increasing your system size, that will increase the entropy proportionally. Right? Where lambda is greater than 0. All right, the last property I want to mention has to do with the concavity of the entropy function. Right? As we saw earlier, I'll say this first. If we take the second derivative of entropy with respect to some variables y and z, that second derivative should always be less than or equal to 0, where our x variable in the second derivative is either internal energy, volume, or number of molecules, and y and z are the other two variables. All right? And so what this at least statement is saying is that we know that when a system reaches equilibrium, the entropy is maximized, right? And so if it's maximized, that means that if you take the, if you're looking at the maximum of some sort of function, the second derivative of that function with respect to a variable should give you a sort of negative number, right? So that would tell you that you're looking at a maximum. Okay? All right, and so in this video, I'm just kind of stating here the rules that apply to entropy. But as far as proving or justifying why these rules exist, this is something we're going to do throughout this course. So we'll derive these properties from first principles. Later on.